Welcome to the Super Science Show.
Today we will be discussing concentration and time dependency. In order to begin to learn this interesting topic, you must understand the basics.
For starters, you must understand that the time is directly related to the concentration.
Therefore, as the concentration of a substance increases, its time of reaction becomes faster.
By the end of this lesson, you will be an expert, like myself, on first-order reactions, second-order reactions, and the half-lives of each.
To further clarify this objective, we will now turn to our friend from the vocab department to explain some key definitions that will be used in this lesson.
Thanks, Sam and Caroline, and hey guys. To make this lesson easier to understand, I will share with you the definitions of some key terms that will be mentioned by our professors throughout the show. Concentration. Concentration is the amount of a substance dissolved in another. Half-life. Half-life, or T subscript 1/2, is the time required for the concentration of a reactant to decrease to half of its initial concentration. First-order reaction. A first-order reaction is a reaction whose rate depends on the reactant concentration raised to the first power. Second-order reaction. A chemical reaction in which the rate of a reaction is proportional to the concentration of the two reacting molecules. In our case, the simpler type involves only one kind of reactant mole, raised to the second power. Natural log. Natural log is the logarithm to the base e. E is a constant equal to about 2.71. Alright, now make sure you keep these definitions in your mind to ease the complications of this topic. Having a good understanding of key vocabulary will create an easier start in understanding. Now we're going to talk about some math next to our equation. We know that a linear equation is set up as a y equals mx plus b form, where b is equal to the x or the y-intercept, m is equal to the slope, and y and x are our variables, as shown on the graph. So, this is our equation for a first-order reaction, where the natural log of the concentration is equal to y, where negative k is our constant, and that's the decreasing slope, where t is our x variable, it's the time that's passed, and this is our initial starting spot, where we start. That's our intercept.
Okay, now I'm going to demonstrate to you how you do a first-order reaction problem. The problem is, if the initial concentration of cyclopropane was 0.25 molar, what is the concentration after 8.8 minutes where the rate constant is 6.7 times 10 to the negative 4 in seconds? So because in this problem the time is given to us in minutes, we need to change it to seconds because that's what our rate constant is in. So all you need to do is 8.8 minutes times 60, and you will get 528 seconds. So now, this is the equation we're going to use for the problem, and it's natural log final concentration, and concentration you can see is dependent on t, time, equals the negative constant multiplied by time plus the natural log of the initial concentration, and that's what the 0 here stands for. Okay, so we have natural log concentration T equals negative 6.7 times 10 to the negative 4 multiplied by time, which is 528 seconds, plus natural log in the initial concentration, which is 0.25 molar. So when you plug that onto your calculator, you will get this. Okay. And this can be rewritten as e to the negative, oops, I wrote that wrong. It's 1.74. And it can be rewritten as e to the negative 1.74, and then that will come out to equal 0.175 molar. And this is the concentration after 8.8 minutes.
Hi, welcome to the second day of the Super Science Show. Today we're going to be talking about second-order reactions. In a second-order reaction, the way that you can test if it's second order is you have a concentration which is still just written like this, as your concentration, except to test if it's second order, you put it 1 over the concentration. So, if you put 1 over the concentration and get an increasing slope, then you know that it's a second order reaction and not a first order reaction. In the second order reaction graph, we can see that as 1 over the concentration increases, and time also increases. So they're directly related. We know that our linear form is y equals mx plus b for a linear equation. So in order to make a graph easier to read in second order, we can put it into that same form, where y is equal to 1 over the concentration. K, which is our constant, is now positive. It's increasing slope, which is m, also equals slope. T is our x variable. So on the x-axis, you see the t. And then the y-intercept is just the starting value. So whatever you start your experiment.
Hello, this is Professor Sam, and today I'll be teaching you how to complete a second order reaction problem. The problem is, this reaction follows second order kinetics and has the high rate constant 7.0 times 10 to the 9th 1 over molar per second at 23 degrees Celsius. If the initial concentration of iodine was 0.086 molar, calculate the concentration after 2.0 minutes. We'll be using the second order reaction equation, which is 1 over the final concentration equals the constant K times time plus 1 over initial concentration. When we plug in all the numbers, we get 1 over A equals constant, which is 7.0 times 10 to the 9th 1 over molar per second, as we see from the problem up here. We multiply this by 120 seconds because we see that it's given in minutes, but for the rate constant, it's in seconds, and we want seconds to cancel out to get a final answer in molars. And finally, we add 1 over 0.086 molar, which was the initial concentration of iodine. When we isolate for the final concentration, we get that this comes out to 1.19 times 10 to the negative 12 molar. And that is the answer to a second order.
Now we're going to discuss half-life. As Ziggy said before in our vocab section, half-life is the period of time required for a concentration to be reduced to exactly 1/2 of its initial concentration. As you can see here, the two half-life equations for first and second order reactions. T subscript 1/2, or half-life, is equal to 0.693 over K in the first order reaction. As Ziggy discussed before, K is a constant. In the second order equation, T subscript 1/2 is equal to 1 over K times the concentration. The main difference between first and second order half-lives is that the concentration does not affect the half-life of first order reaction.
I'm Frigid, and I'm the mathematician on the Super Science Show. Today, I'm going to talk to you about an example of a half-life problem using the first order reaction equation. The problem is, the decomposition of ethane, C2H6, to methyl radicals is a first order reaction with a rate constant of 5.36 times 10 to the negative 4 s to the negative 1 at 700 degrees Celsius. Calculate the half-life of the concentration in minutes. So, how we would start this problem? We would write our equation, T subscript 1/2, which represents half-life, equals 0.693 over constant K. In this problem, you can see right here, it gives us the constant, and the constant is 5.36 times 10 to the negative 4, and then s to the negative 1. And all the s to the negative 1 is representing seconds. So once we do that out, we get T subscript 1/2 equals 1,292.9 seconds. But because this problem asks for the half-life of the concentration in minutes, you have to take this number, divide it by 60, subscript 1/2 is equal to 21.5 minutes. And that's how you would do a Halflife problem.
Hello, this is Professor Sam, and today I'll be teaching you how to complete a second order reaction Half-Life problem. The problem is, this reaction has a high rate constant of 7.0 times 10 to the 9th 1 over molar per second. Knowing the constant, calculate the half-life if the reaction of the initial concentration of iodine is 0.60 molar. So we write T to the 1/2, which just stands for the half-life, equals 1 over the constant 7.0 times 10 to the 9th 1 over molar per second, multiplied by rate of iodine, 0.60 molar. When we put this in our calculator, we find it to be equal to 2.38 times 10 to the negative 10th molar. And that's how you complete a second order reaction half-life problem.
To conclude this segment, we must touch up again on the key concepts mentioned by our professors. You may want to take notes as it is crucial to understand this topic and almost impossible to remember everything that we mentioned.
Let's start by discussing the graphs we explained earlier. As Ziggy explained, a general time versus concentration graph is represented by a curved line.
However, in order to make this line more clear, scientists will take the natural log of each concentration and attempt to create a straight line. If the line does appear straight after taking this step, the reaction is a first-order reaction.
However, if the graphs did not take a straight line after taking this step, you must go further. The next step would be to divide 1 by the concentration. If doing this creates a straight line, you can tell that this situation is a second-order reaction. However, as opposed to the negative slope portrayed in the natural log first-order graph, the slope of this graph is now positive.
The next thing to remember is half-life. A half-life is the period of time required for a concentration to be reduced to 1/2 its initial concentration.
The equation for a first-order half-life reaction is T subscript 1/2 equals 0.693 divided by the constant K. For a second-order reaction half-life problem, it's T subscript 1/2 equals 1 over the constant K multiplied by initial concentration.
However, regarding half-life, it must be noticed that concentration is not a factor in determining the half-life of a first-order reaction, and only plays a role in determining the half-life of a second-order reaction.
On that note, we would like to conclude this segment of the Super Science Show. Stay tuned and always remember that while a reaction may vary between first and second order, as time changes, concentration will continue to change as well.
Until next time, this is Science Sam and Chemistry Caroline wishing you a fantastic day. Stay tuned for upcoming episodes as our other professors will help you to help continue to expand your chemistry knowledge.